dynamics homework problem of the semester. It's a doozy. We got this hammer and it's going to swing down, it's going to hit this ball, and we're going to find out the distance it goes, and then we're going to figure out how high the hammer is going to end up coming. All right, so it starts from horizontal and is released from rest. And when it gets to the position of 30 degrees right here with this itty bitty tiny little angle, the hammer, it hits this ball. And the handle is 1.5 meters long, it's 2 kilograms, and the block is 0.25 meters wide, 0.1 meter tall, and has a mass of 6 kilograms, right? And the hammer strikes the ball at the center of the face of the thing, and this ball is on a frictionless surface, and the ball is 75 millimeters in diameter. It doesn't matter what the diameter is. And 0.5 kilograms mass. Its center is 1 meter from the ground, right? So there's YE right there. And the coefficient of restitution between the ball and the hammer is 0.9. And we want to find the distance that it travels after impact and first hits the ground. And we want to find the maximum angle that the hammer reaches after the impact. So I have written out the problem one last time. And this is going to be several different things going on at once, right? We're going to have work energy to start with. We're going to use that to figure out what the hammer is, its angular velocity just before it hits this. In order to do that, because it's a rigid body, we want to find the mass moment of inertia. I want to take it about the pin right here. So we're going to go 1/12 for the slender rod, MAB, LAB squared, plus MAB, we have to move it times from the center here to over there, so that's LAB over 2 squared, plus, now we're going to get the block, it's 1/12 MD, and it's going to be H squared plus W squared, that's what you do for a rectangle, and plus its mass, and then the distance we have to move it. So then it ends up becoming this all of LAB plus 1/2 of H, right? So LAB plus H over 2, and that's all squared. And I think we get it all. I went ahead, I'll put all the numbers in here, I don't care. So MAB is 2 kilograms, and this thing is 1.5 meters long, plus 2 kilograms and 1.5 over 2 squared, plus 1/12. MD is 6 kilograms, and the H is what, 0.1 squared, W is 0.25 squared, and this is 6, and the distance is going to move. We use this one a lot, so we might want to just remember it. It's going to be 1.5 plus 0.1 over 2 squared. That ends up being 1.55, so we could just, like, anytime we see this together, maybe we could just take a shortcut. And so our mass moment of inertia is 15.95 kilograms meters squared. Now, we want to do work energy, so state 1 is going to be in this first position. Here's going to be state 2. So we'll use work energy. And say that KE1 plus PE1 plus any external work is going to be equal to KE2 plus PE2. KE1 is 0. PE1, all right, so that's going to have us, we're going to have to do a little bit of geometry over here. I did it over to the side. I'm going to need something. I meant to do that before I went through all of this. I see it on my page over there. I need to get the center of mass, location of the center of mass. So I'm going to do it up here. Center of mass, right there. And that's going to be Y bar. And I'm going to measure it from A. It just kind of makes sense. And so we have a summation of the moments not the moment's mass, individual masses and the individual locations of the center divided by the summation of the masses. So I'm running out of room. That's going to be 2, is that's going to be this guy right here, and it's going to be the L over 2, so it's 1.5 divided by 2, plus the 6 divided by that same distance again, that 1.55, so we'll just go 1.55 right there. We know that is. And it's all going to be divided by 8, the total. And that's going to give us a 1.350 meters is going to be the location of the center of mass. I'll write out a heading for this one to kind of like make it a little neater. It's still kind of scrunched up too much. But anyway, okay. So for this, like I said, I wanted to make a little sketch over to the side. And here's where it starts right here. So that's where the potential is. So we're going to have the datum is going to be like down here somewhere. And that's going to be located by the cosine of this theta times that y bar, right? So I'll even make a little drawing of it right here. Right there to right there. Like here's y bar and here's theta. So this is the distance. Originally it's up here, but then it gets down here at the end. Oh no, down here at the end, right there. There's the here's the bar and here's the length onto the side. So here's the actual h. We might call this H1, I guess. So we go mg h1, which is going to be, and that's the total mass of the thing. So mg y bar cosine, I think so. Yeah, just cosine of theta. Running out of room. Maybe I'll make it fit. I don't know. 9.81 y bar, which was the 1 point. We just found that the 1.350 cosine of 30 degrees, and so that ends up equaling 91.75 Newton meters. Okay, so no external work that's going on, no losses or anything like that. KE2, that's the thing we want to find, and that's going to be 1/2 IA omega 2 squared. And we don't have to do anything else because we did this whole mass moment of inertia about the pivot point. And so did I work that out right here? I think I did. Yeah, so, and then also PE2 is equal to 0 because that's where I decided to draw the datum. So putting all those into play, 0 plus 91.75 plus 0 equals 1/2 15.95 omega 2 squared plus 0. And I get omega 2 is equal to, where'd you go? 3.392 radians per second. That's not very fast. I guess I made the thing a little heavy and a little sluggish, but that's what you get when doing dynamics with rigid bodies. Okay, so now I need to do a little bit of kinematics. Let's see, so I'll go kinematics. So we need to relate the velocity at the face of the piece, and I'm going to call that velocity VD2. Right, so VD2 is going to be, let me write this the right way, omega 2 times that L plus H/2, that same guy that we've been using. All right, so he's 3.392 and 1.55, and with that we're able to get 5.257. So that's the face of the block right there where it's about to hit. We want to get a relationship for VD3. We don't know this yet, but we're going to have omega 3 L plus H/2. So we know that's going to be omega 3 times 1.55, and that'll be useful to us a little later. All right, so switching over to another page because we're going to cram it in. I've already been cramming stuff into place, so this is problem 2 continued. Let's make sure this is coming in. Okay, dot dot dot. Let's see. We're going to have our initial impulse momentum. Let me give the headings like I had been doing, which I should be doing that all along. Impulse mom. I saved a little time by writing just mom instead of momentum. All right, so here is it's about to hit the ball. Here it hits the ball. Kaboom. And then it's gone. It's starting to move, right? Let's see. So this is initial, impulse, and final. So this is RA, really the integral RAX dt, and this should be integral RAY dt, cramming it in there. This has the initial IA omega 2, I believe, and this will be IA omega 3, and this is MD VD3. Not VD3, VE3. It's E. So what we want to do is go IA omega 2. Well, okay, so this is conservation of angular momentum. And so therefore we have the sum of the H's about A in, this is case in state 2. It's going to be the sum of the angular momentums about A at state 3. Because all these stuff cancels out right here. These are equal and opposite, and we're doing it about here, so we are able to get rid of those reactions. So we'll write out IA omega 2 is going to be equal to IA omega 3 plus ME, I wrote D before, I meant to be E, ME VE3, and then that's going to be that same LAB plus H over 2, right there, right? So 15.95 times the omega we found just a minute ago, which is the 3.392, is going to be equal to 15.95 omega 3, we don't know that, plus the mass of the ball, 0.5, VE3, and 1.55. Excuse me for a second, I can sneeze. Hope I don't have the virus. All right. Was that something to joke about, is it? Yeah, sure it is. So that's going to be 54.10 equals 15.95. Why are we going to diagonal here? Omega 3 plus 0.7750 VE3. And that's going to be like equation 1. All right, so now we need the coefficient of restitution, right? Because we have two unknowns, and so we need to relate these. And that's going to be E is equal to, let's say it's going to be the ball minus the face velocity. Remember, this has to be right there at the face of the thing. And so VD2 minus VE2. Of course, that one's 0 right there, right? So what we end up writing is VE3 minus VD3 is equal to E times VD2, which ends up being VE3 minus VD3 equals to 0.9 times the face. We got that from kinematics up here, right? So that was 5.257, and your 4.732 meters per second is what that is going to be. So I want to combine that along with, and maybe I should have numbered this one right here though. I want to combine that with this to get it into omega 3, right? So I want to get rid of that D3. So I say VE3, and maybe I'll turn this into equation 2. I'll turn this into equation 1. Right there's equation 1. There. And so with 1, I replace him in there, right? So I go omega 3 times 1.55 is equal to 4.732. And now if I wanted to, I guess I could call that equation 3 at this point. No, maybe I'll do this. I'll solve for omega 3. That's what I did. And so I divided through, and I had to be careful. I think I made a mistake at one point just because I went too fast. So omega comes over to the side of here, and this comes back over there. So it ends up being, I'll do it this way, VE3 divided by 1.55, getting tired, minus 4.732 divided by 1.55. Oof. And omega 3 is then, right out, 0.6452 VE3 minus 3.053. And that I'll call equation 3, right? So now we combine 2 and 3 together. And I'm going to substitute that omega back into that omega right here. So I'm going to start over here to the side. 54.10 is equal to 15.95 times the quantity 0.6452 VE3 minus 3.053 plus 0.7750 VE3. VE3 is then, we are able to find it. Isn't that fortunate? 9.289 meters per second. It jumps right off the face of this thing. And now we could use that and go back into equation 3 and say omega 3 is going to be 0.6452 times 9.289 minus 3.053. So this is going to be equal to 2.940 radians per second is what it's going to be traveling. So it didn't slow down a whole lot, right? It did. This thing, it started at 3.392 just before it hits the ball, and after it hits the ball, it just slows down a little tiny bit. Now we want to do the we have to do the projectile motion. If I had a little more time, I would make this in SolidWorks and see how close I could get. Probably not great, but I bet I could do it. I don't know, given enough time. All right, so we want to have we have a ball that's traveling like this right here, and we know the angle is it's the same as theta, right? Because it's perpendicular to the thing. And so this is E3, and it's starting out at height right here. I think we call this YE. What do I call it? We always YE, right? That height. And it travels and it lands. And for this type of particular problem, we know the initial velocity. I think it's easiest to find the time that it spends up in the air because of the vertical distance, and then go back and find the distance it traveled with that time. All right, so the first things we want to do is get the initial velocities in the x and y direction. So we have VE3. I should probably put a 3 in there. It's not fitting very well. I just want to go home. And cosine of theta, or 9.289 times the cosine of 30 degrees, and that ends up equaling 8.04. I think it's 45. I don't know why, but I went ahead and put 5 sig figs. VE3y, VE3 sine of theta, 9.289 sine of 30, and I get 4.645 meters per second. All right, so we're going to stick on to another page now. It's probably the last page of the semester, though. So there you go. There's something to look forward to. My notes. And this is page 5. Okay. Continued. All right. So what goes up must go down. So we say y is equal to ye plus the velocity of e in the y direction times time minus 1/2 g t squared. So it's going to land on the ground. It starts at 1 meter. YE was 1 meter. Here is the velocity we just got in the y direction. 4.645 times time minus 1/2 9.81 t squared. Now, you modern kids will do the root solver, but I will go, the time is equal to the quadratic equation right here of negative b plus or minus the square root of b squared minus 4ac over 2a. So we have a negative 4.645 plus or minus, and then inside here we have 4.645 squared minus 4 times a. Noteworthy that's 9.81. I guess I'll just write it 1/2 9.81. I just didn't feel like dividing it. Okay, and and c. This is c, right? 1, and then all divided by 2. And by the way, this has to be negative. Oops. So there's negative and negative. Got to be careful there. And same thing here, right? So when we get this and this negative together, this negative is going to cancel it out. So we don't want to get a negative time. We want to avoid that. And I calculated this stuff on the inside. You know, that negative and that negative makes this stuff positive, so we didn't have any risk of it being an imaginary number. That was good. This came out to 6.418. So the 2 times that we would get is 1.128 seconds and a negative 0.1807 seconds. And that's nonsense answer. So here is their answer here. And so now if we want to get the distance, it's going to be the starting x position, which is going to be 0, right? Plus the velocity of E3 in the x direction times time. So coming back up to here, 8.0445 times our 1.128, and I say that it's going to travel 9.072 meters. Wow, what a long journey we've just taken. But we're not done yet. We have to find the angle that this thing is going to keep going, because it keeps going. And I don't know why I asked it, but I thought something I want to know. It also because it does kind of tell you the efficiency, right? Because it started from horizontal, but now it's passed up. It's lost something after the impact, so it's not going to make it all the way up to the next to the horizontal again, because it's lost energy. So we do work energy again. And now we're going to have states. Let's see. Let's call them states 3 and 4, right? So we have KE3 plus PE3 plus the work done between 3 and 4, and we have KE4 plus PE4. Now, some things we know that's going to be true. Well, let's first off, I'm going to do a little diagram over here to the side, right? So here was the thing just a minute ago, right? So here was y bar, and here was that theta. Let's call it theta. Let's call it theta 3, because that's the angle. That's the angle when it's in this position. And then later on, it's going to be up to here, right there. Boom, 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 and that's going to be. I kind of squeeze them in there, theta 4, right? And this also is y bar. So what we're looking at is it's going to make a change right here. This is the H. We call it H4. And that H4, I wrote it out over to the side for me, is going to be y bar times the cosine of theta 3 minus y bar. So that's this length right here. And now we want to have this length right there. We're going to subtract it out, cosine of theta 4. So KE3 is going to be 1/2 I about A omega 3 squared. That comes out to 1/2 15.95 and 2.940 squared. And that's I didn't actually calculate this. I don't know why I didn't. I just didn't feel like it. I guess 2.94 squared 15.95 times 2 divided. All right, so we have 68.93 Newton meters worth of energy taking place right there. And and by the way, we could have gone back early on and saw that that's the efficiency of the thing, right? Because that's the potential energy that at the very start, that's the total energy that was available, right? That's the only thing was potential energy. And now we have at state 3, here's the kinetic energy. So divide those and you'd get the efficiency. But we want to get now PE3. Let's set that as the datum, a new datum right here. So this is the new datum and we're measuring it from here. The work between 3 and 4 is 0. We're going to say there's no outside influences. KE4 is going to be 0, and so PE4 is going to be M times G times H4, which we know to be mg y bar, and then cosine of theta 3, which is 30 degrees, minus cosine of theta 4, which is what we want to find. And we could plug all those numbers in. All right, so this is going to be 9.81. Y bar is 1.350. And we have cosine of 30 and minus the cosine of theta 4. So I put them all in. I don't know what the purpose is of doing that side step right there. I could just, I guess I did. I guess I did write it out. No, I didn't write it out. I'll write it out. 8 and 9.81 times 1.350 times, okay, so that's like 105.9 times the cosine of 30 minus the cosine of theta 4. Oops, make it neat. Theta 4. And so writing all these out for this equation up above, we have 68.93 plus 0 plus 0 equals 0 plus 105.9 cosine of 30 minus cosine of theta 4. And I get theta 4 this time as 77.56 degrees. I did this problem a little while back, and I got like something like 44 degrees, so I'm not sure if I got the right answer this time or not. But what would help is if I did that SolidWorks model, right? So A, the answer is D is equal to 9.07 meters, and B, theta 4, or theta max, that's what we're asking for, theta max was 77.6 degrees. And we are done. And this was a very long video, I'm sure. It's been a very long semester, isn't it? Oh, but so worth it. All right. Thank you, and have a great holiday. Have a great finals week as well.